Next, can we estimate the nonlinear charge transfer resistance or TNL and the polarization resistance. So, this work is published by our group in 2015. Just to refresh your memory, charge transfer resistance is RT and the definition is given here with the inverse of charge transfer resistance right here. At the limit of EAC tending to 0 and omega tending to infinity, that is high frequency limit and small amplitude perturbation, the Faraday current that will not have any phase offset with respect to the potential, okay, and that impedance, Faradaic impedance is inverse of the charge transfer resistance. I am sorry, Faradaic impedance is the charge transfer resistance under those conditions, or Faradaic admittance is the inverse of charge transfer resistance. So, we write it as ZF limit EAC tending to 0, EAC 0 tending to 0, omega tending to infinity, that is charge transfer resistance. I can write it as ZF, I can write it sometime as del E by del I can write it del I for the Faradaic component, I can write it as EAC 0 by IF AC 0, they all mean the same thing. Now, same Faradaic impedance at the limit of omega tending to 0, under those conditions also it will be a real value, it will not have any imaginary component, and that limit the Faradaic impedance is called polarization resistance. Now, if I get rid of this constraint and say EAC 0 need not be small, if I say EAC 0 can be an arbitrary value, large or small does not matter, I would call that as a nonlinear charge transfer resistance. For example, this mechanism, we have an expression for Faraday current, only the first reaction contributes to the electrons and therefore, we write it as F k1 1 minus theta, that is the rate of the first reaction multiplied by Faraday constant. And at infinite frequency we know that d theta by dE tends to 0. Therefore, it is going to remain at theta SS or actually at theta AB, but when it is small theta SS and theta AB are more or less the same. The rate constant k1, if I take the derivative, it is going to give me B1 k1 at that DC potential. So, when I vary the potential close to the DC potential, I will say EDC plus EAC, and when it is small amplitude perturbation, we know that we can write the charge transfer resistance as RT, inverse of RT as F B1 K1 DC 1 minus theta SS. This we have seen before. The theta we write it as average value, steady state value plus d theta by dE, EAC plus and so on. And we know that when omega tends to infinity, d theta by dE will tend to 0. Basically, omega comes in the denominator of the expression for d theta by dE. And theta tends to theta average. When omega tends to infinity, what happens to IF? We can write F k1 1 minus theta and expand the k1 as k1 DC multiplied by e power B1 EAC. Yeah. Now, here I want you to try this. Instead of writing this in Taylor series and truncating after the first term, let us write it in Fourier series. So, we keep the k1 0 e power B1 EDC and call that as k1 DC, e power B1 EAC 0 sin omega t, that I would like you to expand in Fourier series. So, first term is going to be I 0 B1 EAC 0, second term is going to be 2 I 1 B1 EAC 0 sin omega t plus and so on, right, sin 2 omega t or cosine 2 omega t, sin 3 omega, etc., plus minus, all those things will come, multiplied by 1 minus theta average. Now, we want to look at the IF AC 0, that is the coefficient of the response at fundamental, that is at omega. So, we want to look at the coefficient of this, and the coefficient of this is 2 I 1 B 1 AC 0. So, if I write this, I have just copied from the previous page. The IF value is given by the Fourier series. The IF coefficient corresponding to omega is given by f k 1 dc multiplied by 2 I 1 modified Bessel function of the first order B 1 EAC 0 and then multiplied by 1 minus theta average. This is going to be the IF AC 0. If I write IF as IF DC plus IF AC 0 or IF 1 sin omega t plus IF 2 sin 2 omega t sin or cosine does not matter plus phi 2 phi 1 etc. Of course, once I know the value of this coefficient, I can take the ratio and call that as the charge transfer resistance or inverse of the charge transfer resistance. Because I do not make the assumption that EAC 0 is small, I am just using the Fourier series of the full e power a sin theta. I can call this as the nonlinear charge transfer resistance, and that is given by 2 I 1 B 1 EAC 0 divided by EAC 0. So, earlier we would have got an expression saying R T inverse is f B 1 k 1 d c 1 minus theta s s. Now, when EAC is small, theta average is going to be roughly theta s s, and when EAC is small, this value I 1 of x under the limit x tending to 0 is going to be x by 2. This value when EAC is small, it is going to be 2 multiplied by B 1 EAC 0 by 2, and of course, if I take the denominator, this term given in the blue color will tend to B 1 at the limit of EAC 0 being a small value, and theta average will tend to theta s s when EAC 0 is small. So, you can see this expression will reduce to the familiar expression when EAC 0 is small. When EAC 0 is large, this is what you should use to predict the charge transfer resistance. So, what that means is you can write the expression for charge transfer resistance as you would do normally. Okay. Just replace theta s s with theta average and replace all the kinetic parameters B I with AC 0 by EAC 0. So, 2 times I 1 of B 1 EAC 0 by EAC 0. I want you to remember this. This is heuristic, meaning it is based on empirical evidence and based on some expansions for certain mechanisms, and in our experience it seems to work, but this is not proven analytically. Okay. Now, basically what it means is use a correction factor of 2 I 1 B I EAC 0 by EAC 0. This tells how it is going to depend on EAC 0 for each of this B I, okay, and use theta I average, theta 1 average, theta 2 average. You may have multiple intermediate states. For all of them you have to use the theta average instead of theta steady state. Then so far we have been able to predict the RT NL correctly for practically all the mechanisms we have tried. For all the kinetic parameters we have tried. So, earlier we saw that we can estimate the value of theta average when we apply sinusoidal potential. It settles after some time. We found that the wait time necessary is independent of frequency. It depends on the amplitude of perturbation. It of course depends on the kinetic parameters also. We found that we can estimate the average value of the theta. It is independent of the frequency again, but at least under high frequency limit we can show that it can be written in terms of modified Bessel functions. We also saw that if we do not wait for sufficient time and acquire data, then the results are going to be different, especially at larger amplitudes. And we just mentioned that the results taken under those conditions will not be KKT compliant. We did not show that, but we just mentioned that. And we also saw that it is possible to estimate the charge transfer resistance under large amplitude perturbation using a heuristic method that is not proven to be valid under all conditions, but it seems to be working correctly for at least the mechanisms we have tried and the parameters we have tried. Now, can we estimate the polarization resistance under large amplitude perturbation, again without solving the ODE? Okay. Of course, if we can generate the spectrum, then we can just look at what happens to the Faradic impedance when we go to lower and lower frequencies, and when it settles we say that is a polarization resistance. But if I have current, if I have DC current as a function of DC potential, it is possible to estimate the polarization resistance. If I have an expression for DC current, it is possible to estimate the polarization resistance, and I want to describe that part now. Charge transfer resistance is Faradic impedance at high frequencies and under small amplitude perturbation. Polarization resistance is Faradic impedance at low frequencies at the limit of omega tending to 0. That impedance, Faradic impedance, is called polarization resistance. Now, if I get rid of that constraint saying EAC 0 has to be very small, if I say EAC 0 can be large, I still look at the Faradic impedance at omega tending to 0, that we can call as nonlinear polarization resistance. When we want to calculate the polarization resistance, we can write it as EDC plus EAC 0 sin omega t, that is the potential. We have an expression for current, expand in Taylor series, truncate after the first term because it is a small amplitude perturbation, and these are actually approximate signs. Faraday current is split into DC and AC component, and that I can write as DC component here and the AC component here. We have done this before, and we know the expression for d theta by dE comes as B1 K1 DC 1 minus theta SS for this particular mechanism, and the denominator has K1 DC, K2 and j omega gamma. When omega tends to 0, d theta by dE we can write it easily, and IF AC is the second term here. So, we take the second term, this actually is the charge transfer resistance or inverse of charge transfer resistance, this is the addition to estimate the value of polarization resistance. So, we can find the inverse of polarization resistance as RP inverse, and under the assumption this is small signal condition, omega tending to 0, this is independent of omega, this is independent of omega, only this depends on omega, and at omega tending to 0 this can be simplified easily, the j omega gamma goes out. Therefore, we can write an expression for polarization resistance for a given reaction with the assumption that mass transfer is rapid and solution resistance is negligible. Now, for small amplitude perturbation, when polarization resistance is defined, it is easy for us to calculate for any given mechanism. We can calculate the impedance at any frequency, therefore, we can calculate the impedance at 0 frequency or infinite frequency, no problem. What happens when you have a large amplitude perturbation? Okay. We can estimate the DC current for a given DC potential, we can estimate the DC current value, the Faraday current. Okay. So, basically it is this expression with the constraint that potential E is EDC. So, in general for any mechanism you would write as a function of EDC, in this case we know what the function is, what the expression is. When I make small changes, I can say that resulting change, small change is del E, the resulting change is del IF, and if I make the change slowly, that is omega tending to 0, that is inverse of polarization resistance. I can write it in different notations. I can write it as del IF by del E, I can write it as IF AC 0 by EAC 0. Sometimes people also write it as F prime, indicating it is a derivative. Okay. If you have experimental data, I just made this up, IF DC versus EDC. Let us say we do not even know the mechanism, we do not have an expression for this. Still, if I take the derivative here using numerical method, I can take 2 data points, find the del IF by del E, that is find the value of the slope, that slope is going to be di by de, and that is going to be inverse of the polarization resistance. So, this curve which we call as potentiodynamic polarization, the slope of that curve at any given point, that has to be equal to the inverse of polarization resistance. So, if I acquire impedance data here, that data may come like this, it does not matter. The low frequency limit there is RP, and that should be equal to the inverse of the slope of that curve. So, you can take numerical derivative. If you know the form of this Faradaic impedance, if you know the dependence of Faraday current on the potential, you can take derivative, and at the limit of omega tending to 0, you can get the expression anyway. So, it does not require us to solve ODE. Anyway, for linearized cases, we do not need to solve ODEs for this kind of expressions. In 1997, there was a series of publications by Professor Dyard's group, where they have shown even for large amplitude perturbations, one can calculate the polarization resistance, as long as we know the expression IF relating to EDC. Okay. So, when we get rid of the constraint that del E has to be is very small, we can define that as RPNL, and the inverse of RPNL is given by this series. This is the series that they have suggested, and if I remember right, they have used a notation like this. It does not matter, we use a notation saying R subscript P NL. They are given it by a series, and out here F prime indicates the first derivative, F double prime will indicate the second derivative, and F n indicates the nth derivative with respect to potential. Okay. So, f power 2k plus 1 means it is actually not f power, it is nth derivative or 2k plus 1th derivative. B 0 is given as 1, and subsequent b values b 1, b 2, b 3 etcetera can be obtained using this formula. So, if I know b 0, I can calculate b 1, and once I know b 1, I can calculate b 2, and so on. So, this is the expression they have derived. So, which means I need to know the functional form, I need to have ability to get n number of derivatives from this, and when I take more and more numbers, hopefully I will get more and more accurate estimate, and beyond certain limit you may not need this anymore, because this coefficient B k will become smaller and smaller when we go to larger and larger values of k. Now, this has not come very nicely, it is all right. This RPNL, you can take this coefficient and you can rearrange it, and you can show that this expression here is the same as the expression here. Instead of writing in these coefficients, it is pretty much the same. You can give a slightly different format and get the expression for nonlinear polarization resistance. Now, I want you to look carefully. Okay. We want to use a slightly different notation, operator notation. We want to say uppercase D with subscript E would represent d by dE. and that is the derivative. If I write dE power n, that is the nth derivative. So, I want to use this expression operator notation here and substitute here. Second, I want you to recognize or remember this. The modified Bessel function of nth order is written like this: 1 by 2 z whole power n multiplied by this summation, and this of course depends on k value and n value, k going from 0 to infinity. Now, if I take I 1 and if I say I 1 EAC 0 DE, it is going to give me an operator. Okay. I can apply it on a function. DE alone does not have any meaning unless it is applied on a function. Okay. Now, this if I substitute here, I would find it is 1 by 2 EAC 0 DE, and you can substitute in the expression here this 2 power 2 k, k factorial 1 plus k factorial, this 2 power 2 k comes from here, and z power 2 k is EAC 0 DE power 2 k. This essentially is 1 by 2 EAC 0 DE. You can expand this series and you can compare with the terms here. They will basically mean that you can write RPNL as 2 by EAC 0, I 1 of the operator DE, EAC 0 is multiplying the DE applied on to the function f of E. So, we have a function I Faraday current equal to f of E dc, IF dc is equal to f of E dc. If I use this notation, it is a compact notation, this will tell me the nonlinear polarization resistance. So, this part tells the low frequency limit current. So, this tells me IF AC 0 when omega tends to infinity, I am sorry, when omega tends to 0, and EAC 0 is arbitrary. Okay. When EAC 0 is small, I 1 of EAC 0 DE is approximately EAC 0 DE by 2, and of course, when I multiply by 2 divide by EAC 0, I just get a derivative DE F. Polarization resistance inverse of that is DI by DE. This simplifies to the known expression when EAC 0 is small. So, if you have IDC at various EDCs, then you can calculate the polarization resistance, nonlinear polarization resistance, either by taking n number of derivatives, first derivative, second derivative and so on around the DC potential where we want to estimate the polarization resistance. So, in corrosion, polarization resistance basically means at the open circuit potential, but in general polarization resistance it can be acquired at any DC bias. So, it means the low frequency limit of the impedance spectra with or without DC bias. Now, I have an expression IF is given as FK1 1 minus theta. At very low frequencies it is still valid, just that I have to replace the K1 with K1 DC, theta with theta SS, and IF with IF DC. For this, it is possible to write an analytical expression for the nonlinear polarization resistance. We do not need to actually generate various IF values at various DC potentials and take the numerical derivative. It is possible to do it, you can take the numerical derivative, but numerical derivative tends to be noisy, and especially when you go for multiple order derivatives, 5th order, 10th order, 20th order, when you go to higher order derivatives, you would have incorrect result. Okay. Round of error will play a role. Now, if I take E1, E2, E3 and make them very, very small, if they make the intervals very, very small, I get little more accuracy, but again if I make it extremely small, I will have round of errors. So, numerical derivative is something we should avoid if you can. If it is possible to get an analytical expression, it is better to use it. Now, I also want you to notice the following. we have the expression which goes EAC 0 power 2 k and then b k. When you use large amplitude perturbation, you need to use the summation from k equal to 0 to some value, let us say 10. Beyond that you can neglect the terms. If I use larger perturbation, I should go to larger values here. If I go to even larger EAC 0, I could go to even larger value here before I can neglect the remaining terms. So, at what level do we stop? We can't go to infinite summation. Well, actually there are some software which allow you to calculate those values or estimate those values, but in general if you are just writing your own program, it is easy to calculate up to some level and then stop. I want to expand the theta in Taylor series. Theta around EDC, del E d theta by dE, del E square by 2 factorial d square theta by dE square del E cube. This is how we would expand in Taylor series. We would expand around x 0 plus h, this is similar to that. Now, del E we can replace by EAC. So, I can rewrite that as EAC, EAC square, EAC cube and so on. Now, I can't say that EAC is small, therefore, I can't say I can neglect these terms. I actually want to use these to calculate the nth derivative of current with respect to potential. In order to calculate this, I need to be able to calculate the nth derivative of theta with respect to potential, and we are doing some algebra here just so that we can get the expression for nth derivative. Okay. It is lengthy, but again it is not particularly complex, it is not particularly difficult. I can write the k 1, in this case k 2 is a constant. In general I can write k I as k I at dc and then the derivative, first derivative, second derivative, nth derivative multiply correspondingly by del E square del E cube divided by 1 factorial, 2 factorial, 3 factorial and so on. Again I can replace that by k I dc EAC, and the first derivative is going to give me b I, second derivative is going to give me b I square. So, this is actually simple. So, basically I want to take this expression and find the value of d theta by dE. I want to find the value of d square theta by dE square. I want to find the value of d n theta by dE power n. So, I can write this easily, expand it, I can expand this in this Taylor series, I can expand this in the Taylor series, this is a constant. On the left side we have seen this before very early, when we look at the linearization we would have written gamma d theta by dt as d theta by dE multiplied by dE by dt, and we would get j omega gamma EAC d theta by dE. We have done this n number of times. So, we will just continue with this. Now, if I take this equation and substitute without linearization, okay. So, I substitute for k 1 from the expression here, I substitute for theta from the expression here, k 2 is left as it is multiplied by theta. Now, this expression is valid under all EAC. That means, I should be able to isolate the coefficients of EAC and equate them, coefficients of EAC square and equate them, EAC cube and equate them. So, I had to find what terms here will give me EAC square, what terms will give me EAC cube. Right now, I am just focusing on EAC square. Now, look at this, this coefficient, it is a coefficient of EAC square, this is a coefficient of EAC square, this is a coefficient of EAC square. All the cubic terms are given in blue color, but not only that, if I multiply term here with term here, I will get EAC square. If I multiply this term with this term, I will get cube. If I multiply this term with the term here, I will get a cube. So, I have to look at it carefully. Coefficient of EAC alone is pretty straightforward. It can be taken from this multiplied by 1 minus theta, this multiplied by factor here, this multiplied by the factor here and of course, the factor here, and it would give us what we got earlier. D theta by dE is going to be given by the expression we are familiar with, j omega gamma. Now, if we take the coefficient of EAC square, we saw that we have to look at it carefully. Now, I have arranged them or colored them, so that the same colored numbers, if you multiply, you would get EAC square. The pink color, blue color factors and violet color factors, they would give you EAC square. Here the red color factor would give you the EAC square. So, you can group them here. Other terms will give you higher order terms, so we are not going to worry about them. On the left side there is no EAC square, so it is going to be 0. On the right side I would get B1 K1 DC multiplied by d theta by dE. We are taking the EAC square term out and then grouping the remaining terms. K1 DC multiplied by 1 by 2 factorial d square theta by dE square with of course the negative sign, and the violet color B1 square K1 DC and 1 minus theta SS, and of course K2 multiplied by d square theta by dE square. Now, I can rearrange it. You can rearrange it and write basically d square theta by dE square in terms of other parameters, known parameters. I can write it as d square theta by dE square is 2 factorial by K1 plus K2. It is going to depend on d theta by dE. Now, if you look at it, it is independent of omega. Well, it is not really independent of omega. Omega does not appear explicitly here. D theta by dE depends on omega, and of course, we are writing all this under the limit of omega tending to 0. Okay. Now, this depends on theta, it depends on the d theta by dE, and the remaining terms are arranged here. I am going to regroup them slightly differently, but it is possible to show that in general you can do this for the third order. Once you do it for first, second, third, you can look at that and tell that for any nth order, I can write it as n factorial by K1 DC plus K2, B1 raised to the power n, K1 DC by 2 factorial for this particular mechanism, and this entire term on the bracket can be written as a summation with m going from 0 to n minus 1, etc., etc. B1 power n plus 1 K1 DC. This derivative basically it goes from a constant. So, if I say dn by dan of theta, n equal to 0, it means there is no derivative, it is just function theta. N equal to 1, it is the first derivative, n equal to 2, it is the second derivative, and so on. So, this expression for the mechanism given here for any kinetic parameter, as omega tends to 0, this expression is valid. And it is not that difficult to calculate. Once you write a program for this, it is easy to calculate. Only problem is when you want to go to many terms, then n factorial will become a problem. Each operating system and each software, for example, if I want to get 100 factorial in 64 bit, it is possible. If I want to get 1000 factorial, it would give me a number in scientific notation, it will not be accurate. Okay. So, it will have to truncate after certain number of decimals, and it will write in scientific notation. It cannot give me the entire number as an integer unless we have some special program for that. There are some programs which will allow you to change the accuracy, but if I use for example MATLAB, typically there is a limit on what factorial can I get without loss of accuracy. So, basically what it means is I can't just blindly write a program in C or Fortran or any of such languages and then say go to 1000 factorial or 1000 terms. I will have to be aware of the limitation, I have to know under what condition I can get accurate answers and under what conditions we are going to face truncation errors. So, in this we can write the expression for the nth derivative of theta. Now, look at the current value d I by d E. First derivative I can easily write, we have done this before, f k 1 d c b 1 1 minus theta d theta by d E. Now, I just arranged it slightly differently, so that it is easy to generalize later. Instead of writing b 1 1 minus theta, I will write it as b 1 minus d theta by d E minus b 1 theta. I can take the second derivative. If I take the second derivative, this gives rise to, I can say this is u v. So, I take the u dash v plus u v dash, right. K 1 d c, if I take the derivative, I get again b 1 k 1 d c, and this of course remains the same. Here u, it remains the same. This, if I take the derivative, b 1 becomes 0, this becomes d square theta by d E square, square term is missing, and of course, this becomes minus b 1 d theta by d E. I can rearrange it, I can multiply and then rearrange. F k 1 d c, I can keep it outside, retain it, b 1 square, then b 1 square theta, then I have one b 1 d theta by d E with a negative sign, I have another b 1 d theta by d E with a negative sign. So, it becomes minus 2 b 1 d theta by d E, and of course, I have minus d square theta by d E square. And likewise, I can write for third derivative, fourth derivative, etc., but I have rearranged it such that b 1 square is here with a negative sign, d square theta d theta b 1 square theta. So, if you look here, this is b 1 square, this is 2 b 1, no coefficient before that, it is just 1, and this can be written as a binomial series m equal to 0 to 2, 2 m b 1 power m and 2 minus mth derivative of theta. Of course, here n m, that we call it as n c m, is n factorial by m factorial n minus m factorial, and I can write the nth derivative as f k 1 d c b 1 power n. So, essentially I can write the nth derivative of the current in terms of the nth and lower derivatives of theta with respect to potential, and for each of them we have got an expression before. So, we should be able to calculate, and actually if you calculate it for any given AC 0, you would be able to get the polarization resistance value. So, essentially we saw that the polarization resistance can be written in terms of the I 1 EAC 0 d E of the I Faradaic, or we can call it as f of EDC. So, in order to calculate this, we need to be able to take the derivative first order, second order, third order and so on, and in order to calculate those derivatives, we need to be able to take the derivative of theta with respect to potential. Once you have analytical expression for this, for any given EAC 0, we can substitute in that formula, and it does match with the polarization resistance that you would get by solving the ODE and calculating the impedance, what we had done before for the nonlinear impedance. So, the point is it is lengthy, but it is doable, and once you write a program for it, it is actually pretty fast. So, we do not need to solve the ODE, you do need to write a program for calculating these values. So, in summary, in case of simple electron transfer reaction, charge transfer resistance and polarization resistance are the same as long as it is limited by kinetics, assuming that mass transfer is rapid and solution resistance is not high. For other reactions, as long as we can say that kinetics limited and Langmuir-Isotherm model is applicable, we can estimate the polarization resistance. Using analytical expression, basically we can calculate the change in fractional surface coverage with respect to potential, the derivatives, and we can calculate the nth derivative of current with respect to potential. And then using this expression or the equivalent of this expression, we can calculate the polarization resistance. Okay. And in case solution resistance is important, we have to write this as Rp NL plus R solution inverse of this. Okay. Now, what happens if mass transfer is not rapid? Even in that case, as long as we can get the nth derivative of current with respect to potential, perhaps using numerical method, okay, we can still calculate the polarization resistance, we can still calculate the nonlinear polarization resistance. It is just that when you take numerical derivatives, you have to be very careful. Okay. We will stop here today.